All right, let's just jump right into this explainer and demystify what is arguably one of the most mathematically beautiful algorithms in the history of machine learning. We're talking, of course, about support vector machines, or SVMs. Now, if you've spent any time working on classification problems, you already know you've got dozens of algorithms at your fingertips. But SVMs? They're special. They stand out because they aren't just relying on statistical guesswork. They are built on this incredibly rigid, elegant bedrock of geometry. So let's explore exactly how they pull this off. To really grasp the genius of an SVM, we first need to agree on the fundamental problem it's trying to solve. Just picture a map, okay? Imagine you're trying to draw a line between two distinct neighborhoods. Let's say these represent two completely different classes of data points. If you've got a cluster of points on the left and a different cluster on the right, well, there are practically endless ways you could draw a line that successfully separates them. I mean, literally infinitely many lines. So the big question is, how do you choose the absolute best one? Well, the secret sauce here is that we want to build the widest possible street between our two classes of data. We are definitely not looking for some flimsy line that just barely scrapes past the data points. No, we're looking for the one with the biggest margin. And that margin is simply the distance between your decision boundary. Think of that as the yellow line down the middle of the street, and the nearest data points on either side. A wider street means your classifier is way more confident. And crucially, it means it's going to generalize far, far better to new, unseen data. So, for this explainer, we're going to break all this complex math down into 5 quick steps. We'll start with drawing the widest street, move on to those critical support vectors, figure out how to handle noise with soft margins, unlock the magic of the kernel trick, and finally, compare SVMs against deep learning. Step 1. Drawing the widest street. Let's look at the foundational geometry here and see how we actually find that perfect, wide boundary mathematically. What we are essentially building is known as a maximum margin classifier. Assuming we have linearly separable data, meaning stuff you can perfectly slice with a straight line or a flat plane, our goal is to find the specific hyperplane that maximizes the distance to the nearest data points of each class. Because remember, a wider margin means the algorithm isn't just taking a wild guess. It's actually found the safest, most stable dividing line possible, which gives it maximum confidence. Now, to actually maximize this margin, we have to set up a convex optimization problem. Don't worry, we're not going to get bogged down in the algebra today, but the math basically tells us that to maximize the margin, we actually need to minimize the squared norm of our weight vector. That's usually written as the magnitude of W squared. And because this sets up as a convex quadratic program, we get this massive, absolutely massive benefit. It guarantees a unique global solution. There are no local minima traps to fall into here. You get the one true best answer. Step 2. The critical support vectors. Now, this is where things get really fascinating, because in an SVM, most of your data actually doesn't matter at all. And that brings us to the namesake of the whole algorithm, the support vectors. Out of your entire massive dataset, the support vectors are strictly those few training points that sit right on the edge of your margin boundaries. They are literally the only points that determine your decision boundary. Think of them as the absolute VIPs of your dataset. It's kind of crazy, but if you were to move or even completely delete any point that isn't a support vector, your boundary wouldn't change one single bit. The street stays exactly where it is. This really brilliantly illustrates why SVMs are so highly memory efficient at prediction time, especially when you compare them to something like logistic regression. Logistic loss actually uses every single data point to shape its curve, but in SVM, it uses hinge loss. And hinge loss is essentially 0 for any point that's correctly classified and sitting safely outside the margin. It produces a sparse solution. That means only those few critical support vectors have a non-zero contribution. You only have to store those few specific points in memory, not your whole training set. It's incredibly efficient. Step 3. Handling noise with soft margins. Because let's be real, actual real-world data is rarely perfectly separable. We need a reliable way to deal with messy points that land on the wrong side. So to handle this inevitable noise, we have to evolve our maximum margin classifier into a soft margin classifier. A soft margin basically says, okay, we'll allow a few margin violations. And we do this by introducing something called slack variables. You'll usually see this represented by the Greek letter xi. A slack variable is just a way to measure exactly how much a specific point violates the margin. If a point is classified perfectly and sits outside the margin, its slack is 0. But if it's wandering inside the street or totally on the wrong side of the tracks, the slack variable gives us a way to mathematically quantify that error. To control all this, we introduce the C parameter. You can kind of think of C as a nightclub bouncer for your margin.
A large C-value, that's a super strict bouncer. It heavily penalizes violations, which gives you a very tight, narrow margin that tries to perfectly classify everything. The danger there, of course, is overfitting. On the flip side, a small C-value is a much more relaxed bouncer. It allows more violations, giving you a wider, much more forgiving street that might generalize better to new data, but runs the risk of underfitting. It's all about finding that balance.
Step 4. The magic of the kernel trick. Now we are escalating to the actual superpower of this algorithm, because what happens when your data boundaries aren't straight lines, but swirling, highly nonlinear curves? All right, enter the kernel trick. When you reframe all this SVM math into what's known as its Lagrangian dual formulation, you realize something amazing. The entire problem depends solely on the dot products between your data points. And the kernel trick is essentially a brilliant mathematical loophole. By swapping out standard dot products for a kernel function, we can compute the relationships between points in incredibly high, even infinite dimensions without ever explicitly mapping the data to that massive space. It completely bypasses what would otherwise be a devastating computational cost. So depending on the shape of your data, you've got a whole menu of kernel options. The linear kernel is just your standard dot product. The polynomial kernel maps to a space of polynomial combinations. And just to give you an idea of the savings here, a polynomial kernel maps to a feature space of O of d to the power of d dimensions, but computes it in simple O of d time. It's wild. And finally, the RBF kernel. This one acts like a literal magic wand. It maps data into infinite dimensions so it can easily separate and learn virtually any smooth boundary you throw at it. It is pure mathematical magic. Step 5. SVMs versus deep learning. To wrap this explainer up, we've got to address the elephant in the room. SVMs absolutely ruled machine learning from the late 90s right up through the early 2010s. So why exactly did deep learning steal the spotlight? Honestly, the shift primarily came down to two things: massive scale and unstructured data. When you're dealing with giant data sets of raw images, text, or audio, deep learning's scalability easily takes the crown. Neural nets automatically learn features from raw data, while SVMs usually require you to manually engineer those features. Plus, the exact math that makes kernel SVMs so beautiful, it scales at O of n squared, or sometimes even n cubed. So for datasets with hundreds of thousands of samples, SVMs just grind to a halt. Neural networks, meanwhile, scale linearly per epoch and get huge boosts from GPU acceleration. But hey, don't count them out. SVMs are far, far from obsolete. They are still the undisputed champions in some highly critical scenarios where deep learning is frankly just overkill or straight up underperforms. Got a small data set with maybe just a few hundred or low thousands of samples? An SVM will very often beat a neural network. They are fantastic for high-dimensional sparse data, like text classification using TF-ID. They're crazy fast to train in their linear form, they're excellent for anomaly detection, and they are absolutely crucial when you need strict mathematical guarantees on your boundaries, something those deep learning black boxes just cannot give you. By focusing purely on the absolute boundaries, those critical support vectors, rather than getting distracted by the noise of the entire crowd, SVMs offer an incredibly refined, elegant approach to classification. So I'm going to leave you with that thought to ponder. The next time you instinctively reach for a massive, data-hungry neural network for a project, take a second, because sometimes the rigorous mathematical geometry of the critical few is absolutely all you really need.